Alright, this is actually take 2 of the screencast. I screwed up the first one, so here we go again. Hopefully I won't mess this one up for you. So before we go too far, I want to give you a hint for the homework that you're going to be doing in just a moment, because you're going to come across one of the problems that gets you sort of stuck, and I'm going to get you out of that hole of being stuck. So imagine a situation where I tell you that you have, or you've calculated somehow, that you have 0.195 moles of iron and 0.291 moles of oxygen. And as you know, in order to determine the empirical formula, you're going to need to divide both of these mole values by the smallest number of mole values, and in this case, that smallest number is the 0.195. So I've done that, and you're left with these numbers, 1 and 1.5. Now, if I were to put together the empirical formula, it would be Fe1O1.5, which is wrong. You can't do that because you need to have whole numbers. So all you simply need to do is multiply both of the subscripts through by 2, which would give you Fe2O3. There you have it. Okay, so let's move on to the bulk of what it is that we need to talk about, which is determining the molecular formula of something rather than just the empirical formula. Now, just to be sure you understand this, we have something like this, C6H12O6. That's a molecule, and in fact it's a molecule of glucose. And the molecular formula has a 6, a 12, and a 6 subscript associated with each of those 3 atoms. That's not the empirical formula, though. The empirical formula would just be CH2O. So you can understand the difference here is that glucose could not be this. That is not glucose. CH2O is not the molecule. You don't have enough carbons, hydrogens, or oxygens. However, it certainly is the empirical formula for glucose. So we need to move ourselves towards figuring out how to get not just the empirical formula, but the molecular formula of something. And the best way for us to approach this is to have me simply do this through an example. So let me, I'm going to go ahead and erase that garbage that I put there. Don't need that. Imagine the situation where you have a compound that has 56.36 grams of, 56.36%, ooh, that was naughty, of the, let's make this the oxygen component, okay? And I also tell you that the molecular mass for this compound or molecule is 283.9 grams per mole. Now don't forget, that's the molecular mass, and what that means is that if I had the correct number of atoms, so the correct subscripts, for each of the atoms in the molecule, that it would total up, consulting with the periodic table, 283.9. Okay? So those are the 2 pieces of information I gave you. And I also tell you that the other component is phosphorus. So this compound is going to be P something, O something. Now, just like I told you before, when you're determining the empirical formula, you can take the percentage and just change that into grams. So in other words, we have 56.36 grams of oxygen if we were to have 100 grams of this molecule, or this compound. And that would also mean that in turn I would have, for my phosphorus component here, it would be 43.64, which is 100 minus 56.36, and that would be the percentage, right? But I could also then convert that into my 43.64 grams of phosphorus. Then what am I going to do? Got to do the mole conversion piece here. So I take my 56.36 grams of oxygen. My equivalency is 1 mole of oxygen over 15.9994 grams of oxygen taken from the periodic table. And when I calculate this out, it gives me the value of 3.52 moles of oxygen. If I were to do the same thing for my phosphorus, phosphorus has a different molar mass, it's 30.97. But if I did the same thing with an equivalency for phosphorus, I would find that I'd have 1.41 moles of the phosphorus. So 43.64 grams of phosphorus is 1.41 moles. And then if I went ahead and took this information and divided them both by the lowest mole value, which is the 1.41, I would get the value of 2.5 and 1. Now remember what I just told you moments ago. You couldn't have a compound with P1O 2.5. That's not an empirical formula. And I need to, in order to get this, I need to make it into an empirical formula. So I need to multiply both subscripts by 2. So that gives me a true empirical formula of P2O5. That's my empirical formula. With this information, I'm now going to do a new thing, which is I'm going to calculate the formula mass for my empirical formula. And I know that I have 2 phosphorus, and the phosphorus is 30.97 grams when I consult the periodic table. And I have 5 oxygens, and oxygen, as I showed you before, is 15.994 grams. And when I sum these up, I get 141.94 grams. That would be for the empirical formula mass of P2O5. This is where this handy thing comes into play, the molar mass that I gave you in the beginning. Because now I'm going to use that information to determine my molecular formula. I'm going to take that 283.9 grams per mole. It really doesn't need, I should have, I'm going to get rid of that. Just get rid of that. There you go. And I'm going to divide that by my 141.94. Okay, that's what I just got from my calculations here for my empirical formula mass. And when I do that, you can see that I'm going to have a value of 2 that comes out of there. It's not exactly 2, but it's close enough. And that's going to be the factor that I'm going to use to multiply my empirical formula by. Don't forget my empirical formula is this. And I'm going to take this 2 here, and I'm going to multiply through 2 each of my subscripts, which will give me P4O10. And there I have it. That is my molecular formula. And in fact, if you consulted with the periodic table and you did 4 times 30.97, which is the molar mass for each one of the P's, and 10 times 15.9994 grams, you would get 283.9. No surprise there, I hope. Okay, there you have it. Goodbye.